In this video, we're going to look at some practice problems of one-sided limits, limits at infinity, and vertical asymptotes. So first, we have a similar problem like we did in section 1.7. Here's a big graph, and let's just answer some questions about these new limits that we have. So first off, let's look at the limit as x approaches 2 from the negative direction. Right, that's not limit as x approaches negative 2, that's limit as x approaches 2 from the left. So we're approaching 2 from the left, but of course we are looking at the corresponding y values there. And we can see that this limit is going to be equal to the y value of negative 1. The next one is we are going to approach 2 from the right-hand side, or from the positive direction. We're going to look at the corresponding function values getting closer and closer. And again, we are approaching that hole, which is going to be at negative 1. So put those both together, and this tells us that the limit as x approaches 2 has to be equal to negative 1. And we could have done that limit to begin with, just look at both directions, but now we're kind of breaking it up into left and right. All right, now let's look at the limits at infinity. So the first one is the limit as x approaches negative infinity. So that's what's happening with x getting smaller and smaller, and we are looking at the corresponding function values. And we can see that there is a horizontal asymptote here at y equals negative 2. And now we know that that's the exact same thing as this limit as x approaches negative infinity. This is the left end behavior. And this is going to be approaching the value of negative 2. Remember, we are looking for the corresponding y values associated with the x values. When we think about the limit as x approaches positive infinity, we are going to have x get bigger and bigger and bigger. Look at the corresponding y values. And because there's no dotted line there, we're just going to assume that these are going to get smaller and smaller and smaller. It's going to keep on going down forever. And this is going to give us a value of negative infinity. Again, this is what we call the right end behavior. And there is no horizontal asymptote here. All right, and finally, let's look at the limit as x approaches negative 1. I'm going to erase some of the stuff here so we can look at this picture anew. And let's look at the limit as x approaches negative 1. From the left, as we get closer and closer to negative 1, we look at the corresponding function values, and we can see this vertical asymptote that we are getting closer and closer to infinity here. Right, there is a vertical asymptote there. The limit as x approaches negative 1 from the positive direction, however, does not follow that vertical asymptote. It is going to get closer and closer to this solid dot here at negative 2. So what is the limit as x approaches negative 1? Since those are not the same, this limit does not exist. All right, now let's look at some examples of limits algebraically, thinking about what's going on here. So first one, the limit as x approaches 0 of e to the sine of x over cosine of x. So let's think about this using some of the properties of limits that we had before. Note that e to the x is a continuous function. And so what we can do is, first of all, we can write this as limit as x approaches 0 of e to the sine of x over the limit as x approaches 0 of cosine of x. We can do that because we can break up a limit into division and do each part separately. Then, using the fact that e to the x is a continuous function, we can write this as e to the limit as x approaches 0 of sine of x over the limit as x approaches 0 of cosine. And sine and cosine are functions that we should know what's going on. So let's draw a little graph of these functions real quick. Sine looks like this, and we know that as x approaches 0, sine is going to be equal to 0. And this is just because sine of 0 is itself 0. So that means that this limit is 0. Cosine, when we go to 0, starts at 1. We get cosine of 0 equals 1, and therefore this limit will be equal to 1. Now, e to the 0 is itself 1, so this is going to be 1 over 1, and this is 1. Note that that's a lot of work, and what we could have done to begin with is note that or actually what we could say, and we're going to show this in the next video as well, that what happens if we just plug in 0 from the beginning? And we can say that we have e to the sine of 0 over cosine of 0, and this is pretty much what we did. We get e to the 0 over 1, which is just equal to 1. And this is going to be our answer, and this is because e to the sine of x over cosine of x is a continuous function. And we'll say explicitly in the next section, if you can plug in the value that you're approaching into the function and nothing weird happens and you just get a value out, then that's the answer to the limit. We don't have to do anything special other than that because that means that we have a continuous function. If we get 0 in the denominator, if we're dealing with infinity, if something else weird happens, then we have to go into more complicated things. And we can verify that with the limit properties that we had in this section. All right, so now let's look at limit as x approaches infinity of 5e to the negative x minus 4 over 4e to the negative x plus 2. And here we're going to use the properties of limits one more time. So first, we could write this as the limit of the top over the limit of the bottom then we can break it up over additions. This is going to be the limit of 5e to the negative x minus the limit as x approaches infinity of 4 over the limit of 4e to the negative x plus the limit of 2. Now we can use another rule that we can bring the constant out in front. So we can write this as 5 times the limit of e to the negative x. And we know that the limit of a constant is just the constant itself. And same thing here, we have 4 times the limit of e to the negative x plus 2. So this whole problem basically comes down to what is the limit of e to the negative x? And this might help out to know the graph of e to the x, which means that the graph of e to the negative x is the reflection over the y-axis. And this means that as x approaches infinity, y is approaching 0. Another way to think about this is e to the negative x is the same as 1 over e to the x. Think about plugging in infinity. Here we get 1 over, or we think about the limit, it's like 1 over a really big number, which is going to be equal to 0. So this limit is equal to 0, which means that this whole thing is going to be 5 times 0 minus 4 over 4 times 0 plus 2, negative 4 over 2, negative 2. And the properties of limits just allows us to get this problem down to just this limit of e to the negative x. That's the only real limit that we have to do. Everything else just kind of comes for free. All right, next one, limit as x approaches negative infinity of cosine. Let's graph cosine, and let's see what happens to this function. So, as x approaches negative infinity, when we trace the function, what happens? And we can see that the function bounces back and forth between -1 and 1 and everything in between. It's like it's hitting every single value between -1 and 1 forever. So it does not approach one value. So this limit does not exist. In order for a limit to exist, it has to approach one value. This is the exact same reason why the left and right-hand limits have to agree, because if not, then it's like they are approaching two different values at the same time. That means that the limit doesn't exist. It's the same kind of thing. It's approaching all values in between -1 and 1 at the same time, which means limit does not exist. All right, and lastly, we have the limit as x approaches 0 from the positive direction of natural log over x plus 1. And here's a good example of, we know what natural log looks like, we know what x plus 1 looks like, but I have no idea what natural log of x over x plus 1 looks like. So let's use the rule that we can break this up with division and look at both of these limits at the same time. The bottom is pretty easy. When you plug in 0, you get 0 plus 1, which is just 1, and that's going to be the value of the limit. You could graph the function and verify that. You plug in numbers closer and closer to 0 from the right. It's the same thing, but there's nothing weird going on with that function. It's continuous at that point. Natural log, however, does not follow that. We may need to look at the graph of natural log to figure this out. And this is why it's important to know these graphs, or at least some basic properties of the graphs very quickly. So for natural log, when we approach 0 from the right-hand side, we trace the function down, and it's approaching the vertical asymptote here, going down to negative infinity. And I wanted to make clear that, first of all, it doesn't make sense to talk about the limit as x approaches 0 from the left-hand side. Right? And actually, this is the left end behavior of the function. Left end behavior doesn't necessarily mean we go to negative infinity. If the very left end of the function is just going to 0, then that could also be the left end behavior. That's not a super important fact, but it's something that will pop up here and there. Note that our answer is negative infinity over 1, which is just the same thing as negative infinity. So there's our answer there. One last note. Because the domain of natural log is 0 to infinity, sometimes we write just the limit as x approaches 0 of natural log to mean just the right-hand limit. And the reason for that is because it doesn't even make sense to talk about the left-hand limit, so it's just assumed that we're talking about the right-hand limit. This won't happen very often, but it could happen. And if you look at a different textbook or a different material, you may see something like that. So we're going to try to be more careful and just use the right-hand limit in a situation like that.